The strength of a material refers to its ability to bear the load. Strength has the same units and definition as stress. The engineering stress at the onset of plastic deformation is the material's yield strength. The highest engineering stress on the stress-strain curve is the ultimate strength of the material. As mentioned before, the yield strength of the material increases as it is plastically deformed. The ultimate strength, on the other hand, is unchanged by plastic deformation. In general, the yield and ultimate strengths depend on the loading condition. They are different depending on whether the material is loaded in tension or compression mode. The most important two factors affecting the strength of a given material are the temperature and the strain rate, which is the rate at which the load is applied to the material. The strain rate is measured in units of strain divided by seconds. Because the strain is unitless, this would be 1 divided by seconds. The graph shows the ultimate tensile strength of aluminum versus the strain rate for various temperatures on the log-log plot. What can be readily recognized from the graph is that, as the temperature increases from 30 degrees to 1000 degrees, the ultimate strength decreases. Furthermore, as the rate at which the load is applied increases, and hence the strain rate increases, the ultimate strength also increases. This phenomenon is known as strain rate hardening. The yield strength follows similar trends with respect to the temperature and strain rate. Hence the yield strength decreases with temperature and increases with strain rate. Ductility is the amount of plastic deformation that the material can undergo prior to fracture or prior to the onset of necking. For metal forming applications, since once necking occurs the workpiece starts to deform non-uniformly, only the plastic deformation prior to necking is usually considered when measuring ductility. Ductility is measured in this case by the percent of uniform elongation prior to necking, which is equal to the length of the specimen just prior to the onset of necking minus the original length of the specimen divided by the original length of the specimen times 100. In other words, the percent uniform strain is equal to the engineering unit strain just prior to necking times 100. The percent total elongation is the engineering unit strain at fracture times 100. The material is ductile if it has a large percent elongation value, such as most plastics, steel alloys, aluminum alloys, and copper alloys. On the other hand, the material is called brittle if it has a small percent elongation value, such as cast iron and granite. Hence, brittleness of a given material means a lack of ductility, and it must not be confused with a lack of strength. The most important three factors affecting the ductility of a given material is measured by the percent elongation are the temperature, the rate at which the load is applied to the material, and the hydrostatic pressure. As the temperature increases, the percent uniform and total elongations both increase. On the other hand, when the strain rate increases, the percent elongations decrease. A third factor affecting ductility is the hydrostatic pressure. This refers to the pressure around the material. As the hydrostatic pressure increases, the percent and total elongations increase. In order to understand why hydrostatic pressure increases ductility, one must first realize the reason why a material fails or fractures. Materials fracture because cracks and voids that are present inside the material grow and coalesce as the material is deformed. In a phenomenon known as pressure-induced ductility, hydrostatic pressure tends to suppress the growth of these voids and cracks. Hence, a brittle material that is placed under a very high hydrostatic pressure can undergo a large percent elongation without fracture. Toughness measures the amount of energy that a material can absorb under impact loading conditions. The modulus of toughness is equal to the area under the entire stress-strain curve up to the point of fracture. The modulus of toughness is the amount of energy per unit volume that the material can absorb prior to fracture. It has units of newtons per meter squared. Hence, toughness can be thought of as depending on both the strength and ductility of the material. For example, when testing two materials that have the same ductility and similar loading conditions, the material with the higher strength will have a larger toughness. It should be noted that the modulus of toughness measures the energy absorbed by the material when it is slowly loaded at room temperature, in tension, with no notches that cause stress concentration points. The actual energy absorbed by a specimen prior to failure, on the other hand, would vary greatly depending on the temperature, the rate of loading, the loading condition, and the existence of stress concentration points. Hardness measures the resistance of the material to permanent indentation under a static or dynamic load. It can thus be correlated with the ultimate tensile strength of the material. The relationship for many materials between the ultimate tensile strength and a given hardness number is linear, and usually involves the use of a single conversion constant. Another material property that is derived from hardness is a material's resistance to surface wear. The most important factor affecting hardness is the temperature, where similarly to the ultimate strength, as the temperature increases, the hardness decreases. This is important for machining applications since the material of the tools used in machining can lose their hardness under high temperature. The high temperature can be caused by improper cooling of the cutting tool, or excessive tool speed and slash or feed rate. Review questions. The steel specimen with a yield strength of 210 MPa, and an ultimate tensile strength of 400 MPa, is loaded in tension to a stress of 300 MPa. After the load is removed, what are the values of the specimen's yield and ultimate tensile strengths in the tension mode? Right answer. For metals in general, what happens when the temperature increases? Right answer. For metals in general, what happens when the strain rate increases? Right answer. For a given tension specimen, which of the following statements is true? Right answer. For metals in general, what happens when the temperature increases? Right answer. For metals in general, what happens when the strain rate increases? Right answer. For metals in general, what happens when the cross-sectional area of the specimen increases? Right answer. What is pressure-induced ductility? Right answer.